Alright, let us begin. ME8508, this is our basic control systems for ME class. We have seen that if I have a linear time invariant system and if I have an input u of t and I have a scalar output y of t, then y of s in the Laplace domain is equal to some g of s times u of s and this is called the transfer function. We have seen this. Now for a system that is given to us, some engineering system for which we write equations, we can write the equations, take Laplace transforms and calculate the transfer function. However, I want to show you that it may be possible to construct systems that have certain transfer functions that we like, and to do that we have to look at something called operational amplifiers, which is a very basic topic from electronics. You may have seen it before. These are also called op amps. You may have seen it before. In case you are interested, you can always look them up. Let's see how it goes here. Suppose I search for op amps. You see there will be thousands of pages and they are shown like this. There is a supply voltage positive and a negative. There is a positive and a negative terminal, and there is an output. And I'm going to tell you something about these things, not because you will become an expert on op amps, but you will sort of understand some possibilities. Okay, so the thing with the op amp, like it's shown like this. So I will write here V plus, that's actually a supply voltage. Another pin is V minus, and there is a plus terminal here and a minus terminal here. The minus allows feedback. So so there will be something here, there will be something here, and there is something here. Okay, so there are two inputs or to the op amp, but one of them you will control in some way. That will be clear soon. And this is V output. Any feedback from here which goes to the input terminals must be like this to this terminal. Okay, no feedback here. This is the basic device. Now what does it do? What it does is it has a very large gain, something like 10,000. We think of it as infinity. Here, let's make it red. Well, I mean this. These terminals take in very small currents. I think maybe microamperes. Okay, I'm not an expert, but we think of it as zero. The result is that when you operate this device in a stable mode, what happens is either this voltage, let me call this V1 for the moment, and let me call this V2. So either V1 is equal to V2 and V out is finite, or V1 is not equal to V2 and V out is saturated. Saturated where? At V minus or V plus. Okay, and we will use the operational amplifier in this mode and do all kinds of interesting things with it. We will not actually use them. We will discuss the possibility of using it in this mode, and you will see that very interesting things are possible. So for example, I will not even draw the plus and minus anymore. Okay, so plus like this over here. Okay, let's say this is my input, this is my V output, and I take this and put it back here. What happens is, if the operational amplifier is working properly, then this voltage, this and this must be the same. That means V out will be equal to V in. What is the use of doing it? This current drawn will be 0, this current will be big. Well, you know, when I say this current is big, you know, it's 10 milliamperes or less, something like that. But even so, that is quite big. With that current you can drive signal transistors, with those you can drive power transistors and so on. So by the time you are in the few milliamperes range, then after that you can do a lot of things with it much more easily. So this is called a voltage follower. Okay, so that means if you have a voltage without drawing any current, you can reproduce the voltage somewhere else where you can draw current. So that is why if I say we will measure the voltage here and put this much current over here, you may use a voltage follower. Okay, let's do another one. Let's put this to what we call 0. Let's put here R1, R2 and V in. Okay, now there is a current in this direction, right? How much is the current? This current is equal to minus of V out minus V in over R2 plus R1. That's the current. Okay, clear, no problem. This is at 0, therefore this point has to be at 0. This means V in minus 0 by R1 is equal to the same current, which means V in minus V out by R2 plus R1. Okay, what that means is let's see, what that means is V in, this should be easier than it looks, V in times R2 plus R1 by R1 minus V in equals minus V out. Okay, you simplify this, it is some multiplying factor. That multiplying factor is easy enough. Let us say V out is equal to V in with a minus R2 plus R1 minus R2 minus R1 over R1. I may have made an algebraic error, but you can check for that and correct for it, but this cancels. That's not right. This is minus R1 only, this is not there. That was the error. This is not there. Okay, so this is just R2 by R1, and so V out is equal to minus R2 by R1 into V in. This is called an inverting amplifier. Okay, so you can take R2 by R1 to be something like 10 or 20 and it will work. You will get a larger voltage over here at the cost of drawing a small amount of current. Okay, now let me show you something a little more interesting. What is a capacitor? So if I have a capacitor, this is a capacitor, right? So it will have a charge Q and it will have a voltage across it which will be V, right? So what is capacitance? Capacitance is equal to Q by V. V is equal to Q by C. Okay. Now what is current? Current is dQ by dt. Therefore, dV by dt times C is equal to I. Okay, so this is a capacitor. Very good. What happens here? I can do this in two ways. Okay, I think the best way to do it is if I compare with a resistor, right? So if I have V is equal to IR, this is the resistance. Okay, now you look here, I will write this as CSV because now I am writing in Laplace domain. S is the derivative. This is equal to capital I. So V is equal to I by CS. Okay, so you see, if this is the resistance, we will call it impedance now. The impedance of a capacitor is one by CS. Okay, what does that mean? If I write in the Laplace domain, if I put a capacitance here and then I put a resistance here, this is my V out, this is my Vn, and this goes to ground. Okay, just like the previous case, now V out is equal to minus R, here this is C, this impedance by this impedance. Remember, that's what we got here. Minus R2 by R1. Only now we will be replacing with impedance. Okay, so you can work it out with differential equations, you'll get the same thing. So minus R by 1 over CS Vn is equal to minus RCS Vn. And I hope you realize this, except for the negative sign, which is easy to correct, right? Change. This is a differentiator. Okay, suppose I do this. Then what I have is V out is equal to minus this impedance, which is 1 by CS, over this impedance, which is R Vn, which is minus 1 by RCS Vn, and this is an integrator. So these are very nice things. Okay, you can do all kinds of things. Now let me just show you one final thing. I don't want to spend much more time talking about it. I hope you understand how op-amp circuits work, and I am not going to do very complex things. You can add things also. Yeah, I'll show you that. But let me do the following. R1, C1, R2, C2. This is V in, this is V out. Now what do I have? Now I have V out is equal to minus R2 plus 1 by C2S over R1 plus 1 by C1S V in. Okay, I hope you agree that that's what it is. And now this becomes basically, let's just look at this term, that's the interesting part. So this becomes R2 C2S plus 1 by C2, the S's will cancel. R1 C1S plus 1 by C1. Okay, you can see the S's will cancel. So that is nothing but A plus BS by C plus DS of this form. You see, now I can add and subtract things. Okay, so if I can add, then I can subtract, because I can invert and add, right? So how to add? Suppose I have a V1, then I put some R, then another R. This is some big R, so it does not draw much current. This is V2. Okay, well, because this is not drawing any current, whatever current is going through here is just going through these resistances. These two are the same. Therefore, this voltage is V1 plus V2 by 2. That means V out is equal to V1 plus V2 by 2. Don't worry about the factor of 2, because you can correct it in principle with another amplifier. Therefore, what has happened is that you have added 2 voltages. Suppose you want to subtract 2 voltages, you can invert one with, that inverting amplifier. You can invert it, and then after that you can add it. So then it will become one minus the other. You can take such a transfer function, which is the output of something, and then you can add, subtract, and multiply. The multiplication part is in the next lecture. Okay, so for this reason, I hope you will agree that with small, simple electronics, these op-amps cost a few rupees. Okay, they're nothing. With small, simple electronics, simple, rational means ratio of polynomials, transfer functions can be realized easily. Okay, so we will stop here.